Hmm. Okay, then yeah. Now 29. Yeah. So let us move to this problem, and before that, please check that whether the slide is changing or not. Wait a minute. So if the slides are changing, PPT, is it happening, pa? Hello?
Your screen is not visible, sir.
Emma?
Your screen itself not visible, sir.
Oh, screen is not shared. Okay, 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 okay. பரவாயில்ல நல்லதாக போச்சு கேட்டது நல்லதாக போச்சு okay so now it is shared now so please see that whether it is changing slide is changing
Yes, sir.
okay thank you okay so uh, last class we have discussed about two degree of freedom system, the derivation and all equation of motion, the derivation, modes of vibration, and so on. And today, with that concept, we will see how one can solve the problem. So please go through this. A two-story shear building has to be analyzed dynamically using the following data. For zone 4 means we know very well, as per the seismic criterion, the total India has been divided into 5 zones. But the first zone is not at all using now because it doesn't have any much influence. So that almost, I mean, it's not like that. The entire India has been divided into even though 5 zones, but first zone is not there. It starts with the second zone to fifth zone. Total 4 zones only actually. Okay, so for zone 4, I equal to 1.5, which is called as the influence factor. You don't worry about this. See, sometimes what happens is in a given problem, some data which may not be important to do this analysis, even then to confuse you or something like that, they may give some additional data. So to solve this problem, this data like zone number or influence factor, influence factor, sorry, it is not influence factor, importance factor. You will understand this zone importance factor and all in when I'm going to discuss in the fourth unit. So don't worry. And then soil, then regarding the soil strata, soil hard rock, they have given the condition of the site. Then damping 5.1. So this data is not important for the time being. Okay. So detailed as per IS 456 seismic weight equal to 100 kilonewton in each story. Stiffness K equal to 50,000 kilonewton per meter in each story. So find the frequency, time period, and mode shape. So as per the 2 degree of freedom system, what we are discussing, we need to find out frequency, that is natural frequency of the system, omega n. We have to find out. So if it is a single degree of freedom system, we used to have only single omega n natural frequency. But if it is a 2 degree of freedom system, we will have two natural frequencies, omega n1 and omega n2. In the last class, we have discussed that. So, and then time period. So once if I know the omega n1 and omega n2, I can also find out the time period t1 and t2. And based on the natural frequencies, one can also find out mode shapes. So you will understand this in the derivation. I don't know how far you people understood that concept, but when you try to solve the problem, probably it will be clear much about this. Okay. So first statement, if you look at it, it is talking about a two-story shear building. So instead of a single story, it has 2 stories, ground floor and the first floor, right? So according to this statement, you have to draw the diagram of this. It's a building, the shear building model, right? And the stiffness. So it is also given that seismic weight is equal to 100 kilonewton in each story. See, basically, when you try to solve this building frame model problems, we have taken the mass to the each floor, like the mass comes from the beams and slabs. And we have neglected the masses for the columns, right? Those things are the assumptions before doing this model analysis. And stiffness is only considered for the columns, not for the floor slabs and beams and all. So, simply speaking, mass is concentrated at each floor level to the beams and slabs. And similarly, the stiffness is considered only for the columns, because the flexibility and all we have taken for the columns only. Okay. So they have given that stiffness K equal to 50,000 kilometer per meter in each story means, this comes from only the columns. The stiffness we have not taken for the beams and slabs. Okay, so with this data, so let me draw the two-story building drawing like this, the line diagram, and masses are shown at the floor levels, and each maybe the slab and beam combined together. Here we have for each floor. Okay, so this is and of course masses we are taking, but the given value is a weight. Of course, even though it is weight is given, one can also calculate the mass. It is not difficult to do it. W equal to mg and m equal to w by z. Weight is given by 9.81. If I put it, I can get the mass and all. So that is not an issue. And each story value. These values are for each story. Please understand. See, here stiffness K is equal to 50,000 kilometer per meter in each story. So I have taken K and K. Sometimes the stiffness of each one story may be different from other story. Then you can take K1 and K2. But each story stiffness means it is combining stiffness of both the columns of each story. Understand that? So in the ground floor, I have two columns. It is not a stiffness of column 1 and stiffness of column 2 separately. Combining stiffness of both the columns in the ground floor is K. Okay. Similarly, combining stiffness of first floor columns will be K. So what it means is actually, suppose if the stiffness of column in the first floor, if each column stiffness will be K by 2 and K by 2. So combining, put together of both the columns, the stiffness is K. So that also we need to understand because in the examination, same kind of problems will not be given. You need to understand, sometimes they may give that individual column stiffness. Then we have to combine all the columns of each floor, by which you can get the each floor stiffness. So that is also very important. So now we have this shear building model. And from this, to analyze this problem, we need to take it as a equivalent spring mass system. So we already had seen yesterday, last class, stiffness comes from the column. See, this is a stiff, this is a fixed one. So let us take this. See, this I have considered in a horizontal manner. You can see that. So the fixed one, then the stiffness is there. Spring I have taken K1. Of course, K1 is nothing but K here actually, because both the stiffness are the same. First floor also. So then I have the mass M1, first floor mass M1. Then the next floor, first floor, ground floor, first floor is the mass M1. Then next one we have the another column, right? First floor column. So the stiffness is K2, and second mass, the topmost mass is M2. Of course, in this problem it is given as M only, but in generally I'm taking like this: M1, M2, K1, K2, and X1, X2, right? So displacements, so here for the first mass, the displacement is given as x1, second mass displacement is given as x2. The same thing we have considered here, right? So now I have replaced that K1 by K and K2 by K, because that is what is given in the problem. Similarly, M1 by M and M2 by M. Of course, the displacements are x1, x2, like this. So now if you write the, if you draw the free body diagram of each mass, so first mass is M here, and for which I have the left hand side the spring force kx1 and inertia force mx1 double dot, and in the right hand side I have another spring here which has a stiffness k. But I already told you that when you consider this second spring, we need to consider what the second spring is connected by two masses, second mass and the first mass. So farthest end displacement is, I mean, the front side displacement of the k, I mean, the second spring is x2, and backside displacement is by x1. So for which, for the spring k, we will get a relative displacement. So k into x2 minus x1. So with that only, we'll have a spring force here to the first mass, right? Similarly, if you draw the free body diagram of the second mass, extreme right side mass, we'll have only the spring force k into, yes, of course, x2 minus x1 only. Then we also have the inertia force, which is mx2 double dot, but in the right hand side, nothing is there, just you leave it. So from the first mass, I can write the equation of motion like this. Equation of motion. So mx1 double dot plus kx1 left hand side forces. So this is acting right hand side, so that minus k into x2 minus x1 is equal to 0. Okay. Similarly, for the second mass, equation of motion is mx2 double dot plus k into x2 minus x1. Nothing there is there in the right hand side, is equal to 0. That's all. But you have to you have to remember that after writing the equation of motion for both the masses, we have to rearrange these equations in such a way that first mass component related thing, then second component is what are the constant coefficient values for x1 that we have to separately do it. Then what are the constants multiplied by for x2 that you have to separately write in the third term like that. So x1 multiplication, x2 multiplication, so that it is easy for us to bring into the matrix form. So now I have expanded this the first equation mx1 double dot plus kx1. The second one is if c minus kx2 minus into minus plus kx1. Okay. So anyway, I have written as such here, but here if you see here rearrange the above equation, mx1 double dot plus c here minus into minus k minus into plus kx1 and here kx1. So 2 times of kx1. So that is why you have taken rather 2k into x1. So first x1 multiplication, whatever is there, that you have to write. But in this fashion, it is different. You see, the style of writing is different. This is only from the free body diagram we got it. So we are always trying to get only from the free body diagram like this, but it has some kind of a combination of a mixture of x1 and x2s. That what you are trying to do is you are separating out the x1 coefficient and x2 coefficient separately, so that to write that in the easiest manner in a matrix form. For that sake only you are trying to do it. Then x2 multiplication, what we have only minus k. So minus k x2 is equal to 0 from the first equation. Similarly, second equation also the same fashion. So first mass component, inertia thing, that is mx2 double dot. Then see x1, first one the multiplication, x1 multiplication, you have to write. So minus k x1 in the second equation I am talking about. Then plus x2 multiplication is k, x2 is equal to 0. So we have these two equations. After getting these two equations, now one can write the matrix form of these equations, right? So if you see the matrix from a mass matrix, so m into x1 double dot is there, acceleration. Fine. So m into x. So if you do the multiplication of this mass matrix and the acceleration vector, m into x1 double dot plus 0 into x2 dot, because x2 double dot. So in the first equation, I do not have the second acceleration component. So x2 double dot is not there. So that is why, even though you're writing here the acceleration vector, since in the first equation there is no there is no acceleration component of x2 double dot, but you can write the x2 double dot by putting a 0 here. So when you multiply these two, m into x1 double dot plus 0 into x2 double dot, anyway x2 double dot vanishes here, right, in the first equation. So that is how we can write. Similarly, for the second equation, if you see, I have the multiplication factor for the second acceleration, x2 double dot only. But there is no x1 double dot in the second equation. That is why 0 into x1 double dot. So first component of this mass matrix in the second row is 0. Then second element is m into x2 double dot. So it satisfies the second equation, right? Okay, so this form. So always mass matrix, if you look into the mass, look at the mass matrix, always we'll get the diagonal components. Like so even though it is 2 by 2 matrix, I have m and m. If I have 3 by 3 matrix, like let us say 3-story building, so probably you may have another mass, but by which all other elements, upper triangle and lower triangle elements, are going to become 0. Okay, so we will have only diagonal elements for the mass matrix, right? So once you have been thorough with this, it is easy only. Initially, it may look like a little difficult, but it is easy only. Once you practice it, it's very easy. So plus second matrix, you look at it. So first I am writing the displacement vector x1 and x2. But in the first equation, you see what we have. So 2k into x1. So 2k into x1 minus k x2. So minus k into x2. So here minus k is there. The second component of the stiffness matrix. Then the second equation, the first element is should be multiplied with x1. So that is minus k. Then for the x2, it is k. So simply speaking, when you write these equations in this standard form of x1 multiplication first, then x2 multiplication next, simply what are the multiplications we have in the first equation? That is multiplications means that is stiffness values and all. You can simply write in the first row of stiffness matrix. You see 2k here and minus k minus k. And from the second equation also, x1 multiplication is minus k here and x2 multiplication is k here. Provided the sequence it has to follow. You should not write like for example, you take a second equation. If you look at the very beginning of the second equation and after free body diagram, it has with the k into x2. First, if you simplify it, what we get is k into x2 minus k x1. But if you write like that, definitely you may end up with the wrong things and all. So first, always try to write the coefficient of stiffness, which is multiplied with x1 displacement, then x2. So that order should be followed. Then it is easy to write the stiffness matrix 2k minus k minus k k. Simply you can write it. You need not check that into x1 whether I'm getting it or not, like that. So please try to follow in writing the equations of motion in an order, in that order, that is x1 first and x2 second and like that. Then it is easy for you to write this stiffness matrix also in the correct form. Is it clear? Okay. Yeah. So with this, we got the mass into acceleration plus stiffness into displacement equal to 0. That is the form, general form. But solution of the equation of this motion is, we know x1, just let us assume that capital X1, that is initial amplitude. Capital X1 is initial amplitude. This is small x1 is with respect to time, how it is moving, right? So initial amplitude into cos omega nt. So cos function, we assumed that vibration as a like this. So similarly, x2 also, some capital X2, some other amplitude is initial amplitude into cos omega nt. So both are cos functions we have taken. So if I do the differentiation of this one with one time, we'll get a minus x1 omega n into sine omega nt. If I do it one more time and x1 double dot, so we'll get omega n will be multiplied one more time. So omega into omega n square, minus already there. So x1 into what you get is the sine becomes now cos omega nt. Second time differentiation, understand that this is x1 double dot, not single dot. So 2 times I have differentiated the first equation of the displacement, by which I got it as minus omega n square x1 into cos omega nt. Similarly, do the differentiation for 2 times with the second equation also, will get like this. So, but if you look closely, watch this, simply the acceleration, the first acceleration, still it is a function of displacement only. What I'm getting is minus omega n square into x1, because this capital X1 cos omega nt is nothing but x1 only, right? So into x1, and here also x2 double dot also minus omega n square into x2. So if you write that, and once again, whatever you have the previous equation, mass matrix, into small x1, small x2, x1 double dot and x2 double dot is there, no? So I'm replacing with this minus omega n square x1 cos omega nt minus omega n square x2 cos omega nt. Plus stiffness matrix into the displacement x1, x2 is with x1 cos omega nt and x2 cos omega nt. So now if you simplify this, that, what happens is, so rearranging the above equation, because in both the equations, in both the terms, I have x1 cos omega nt for the mass matrix multiplication, and similarly stiffness matrix multiplication also x1 cos omega nt, the common factor is there. Similarly, the second one is x2 cos omega nt is a common factor for both the mass matrix multiplication as well as stiffness matrix multiplication. So that you can take it outside here. So cos omega nt, if I take outside, what can I get is minus omega n square into capital X1. I'm sorry, I think this is capital X1, not a small x1, it's a capital X1. So I have to change this. I think even the last class, while deriving the equation also, I did a mistake there. So it's a capital X1 and it's also capital X2, right? So minus omega n square. See here, see 2k stiffness matrix minus omega n square into mass matrix. And the minus term, so that we are written in the second term, right? So first stiffness matrix minus omega n square into mass matrix. Of course, x1, x2, capital X1, I'm sorry, and capital X2 cos omega n equal to 0. So this is what we got at the end. But see, is equal to 0 is there in the right hand side. To get it as a 0, we have to see that which term could be 0 in this. Like, let us say if I take the cos omega nt is equal to 0, it is possible. If I take cos omega nt equal to 0, in the right hand side equation becomes 0, because 0 into something is 0 only, fine. But practically, if I take the cos omega nt as 0, what happens is 0 into x1 is 0. So finally, there is no displacement at all. So the mass is not at all moving. If there is no displacement, there is no vibration. So we cannot analyze this problem like that. So practicality is it has to vibrate. To vibrate, definitely we have to have that cos function. If cos function becomes, entire thing becomes 0, entire the displacement is going to become 0. So that is not possible practically. Therefore, the only possibility is what are the multiplication of other factor is there, that could be 0 for a non-trivial solution. Okay, so thus for non-trivial solution of x1 and x2, the determinant of coefficient of x1 and x2 must be 0. Now, whatever we have got, x1, x2 multiplication, the determinant of this one is equal to 0 for non-trivial solution. So that is why you can put a mod of multiplication factor of x1 and x2 is this one. That is a stiffness matrix minus omega n square into mass matrix. Determinant of that is equal to 0. So now we have the 2 by 2 matrix in both the terms, and we need to simplify that. And before that, now we can substitute what are the mass values and the stiffness values are given in the problem. Okay. So in our problem, the seismic weight is given as, and don't you forget about the zone number 4 or what is that, importance factor, all those things, and all those things are not required to analyze this problem in this manner. Like what we are trying to do is only finding out the natural frequency and mode shapes of the vibration and the structure wherever it may be. So we are not going to bother about that. So with the given seismic weight and stiffness and how the natural frequency and how could be the mode shapes and all, that's all we are trying to analyze here. So therefore, you leave the other data as such, and then the remaining rest of things are seismic weight is there. So from the weight one can calculate. So I have to convert into mass here. See, mass, if I take outside 1001, so that's all here you are getting. So mass, how do you get the mass from given weight? Weight by z, and weight also given in kilonewtons. That you have to convert into newtons by multiplying with the 10 cube here. You please notice here 100 into 10 cube divided by 9.81. So with this, I got the mass from the given weight. Similarly, stiffness also, it is given in kilonewton per meter. Always we are trying to take the stiffness in newton per meter. So into 10 cube. So 50,000 into 10 cube. So stiffness also you can take it outside from this. Then inside the matrix will be 2 into -1, 1 like that. Okay, k if I take k outside. So this you bring it to the right hand side. The determinant I'm trying to do. So whole divided by 50,000 10 cube if I do, I will be getting in the second component like this, omega n square into that we need to simplify. And if I simplify it, and I got it as 2.03 10 to the power minus 4 omega n square. So for easy simplification process, this entire thing of 2.038 10 to the power minus 4 omega n square is, I'm taking it as I'm assuming it as some lambda, something like that, something lambda, gamma, rho, whatever it is, you can assume something, because these are all only for easy simplification process. Okay, so this I'm taking it as a lambda, let us say. Now we can modify that. 2 minus lambda into 1 lambda, fine, the first term. Minus 1 minus lambda into 0 is 0, so only minus 1, second term of the first row. And second row, you see, the first term, minus 1 minus lambda into 0, anyway 0, minus 1 only. Then the second element of the second row, 1 minus lambda into 1 lambda, right? 1 minus lambda. And mod determinant of this equal to 0. So 2 by 2 determinant we know, AD minus BC. So 2 minus lambda into 1 minus lambda AD minus of BC minus 1 into minus 1 is equal to 0. Okay, so determinant is 0. And with this, we are trying to get a quadratic equation for lambda. So lambda square minus 3 lambda plus lambda equal to 0. So if you write the solution of this, we know for a quadratic equation, x square plus bx plus c equal to 0 and x equal to minus b plus r minus root of b square minus 4ac by 2a. If you do that, you'll be getting two solutions. Minus b plus r minus is there. Now, if I use the plus sign in between the both the terms, I will get one value. If I use the minus sign, I'll get the other value. So we have got the two values for lambdas. Okay. So once after getting this lambda, because ultimately we need to focus on natural frequency, not the lambda. Just only for easiest simplification process only, this some constant into omega n square you are taken it as a lambda. The square term under I don't want to bring it here. So that is why for easy simplification process only I assume some other thing like lambda, rho or gamma, something like that. But ultimately that is equal to, see, finally we need to get what is the omega n. So lambda, if I take one value, okay, so 2.03 10 to the power minus 4 omega n square equal to lambda 1 if I take, and the lambda 1, let us say 0.381, and try to find out omega n1. So for each lambda, we can find out the each frequency, corresponding frequency. So from this, we can get the omega n1 as 43.32 radians per second. I'm sorry, I forgot to mention that unit here, radians per second. And from that, because in the problem, they asked us to find out this frequency as well as time period of oscillation. So T1 equal to 2 pi by omega n1, we know from physics. So it is nothing to do with the dynamics. It is only from physics. 2 pi by omega n1 is equal to 0.145 seconds. So we got time period for the first natural frequency. Similarly, if I do the lambda 2, if I substitute in this equation, 2.03 10 to the power minus 4 omega n2 square is equal to lambda 2. You do that. Lambda 2 here, I can get the omega n2, right? So 113.56 radians per second. Then time period equal to 2 pi by omega n2, I got 0.055 seconds. Fine. So once after getting this, now we are moving to the end of this problem. So mode shapes. So we found out natural frequency, time period, and then mode shapes. So we are coming to the last stage of solution of this problem. So let us take the first lambda, which is the lowest value, 0.381 for first mode. So whenever we have the 2 degree of freedom system, we'll have two modes of vibration. If I have 3 degree of freedom system, we'll have three modes of vibration. We'll see that how it looks like and all. So probably this thing you may not, I mean, I think you have not understood clearly when I was trying to derive these things and all. But probably now we can understand what is this mode of vibration and all. So as such, 2 minus lambda 1 minus 1, whatever we have in the previous equation, please see that. One second, I will go back to this and what we are trying to do. So this mod inside is there, no? Mod inside is there, no? So that you can write it as a that is a matrix form. 2 minus lambda 1 with the first lambda. Minus 1, 1 minus lambda 1. Okay. into phi 1, phi 2 we have to put. You see that. So phi 1 of and phi 2. These are all the modes actually. Since I'm trying to use only first lambda, and for both the phi 1 and phi 2 top, what we can write in the brackets as the first, which represents the first mode of vibration. Okay. So is equal to 0, 0. Yeah, so now we can multiply 2 minus lambda 1, you can substitute here 0.381. With this, we got 1.619 minus 1, and 1 minus lambda 1 0.381 is 0.619. And as such, phi 1 and phi 2 is equal to 0, 0. Now, what we have to do is we can multiply these two. So 1.619 into phi 1, 1 minus 1 into phi 2, 1 is equal to 0. Likewise, second also, if you want, you can write second also, not required. So 1 is enough. First itself is enough. Okay, so but here, what we have to do is we need to assume something like either phi 1 is equal to 1 unit or phi 2 is equal to 1 unit, which means if the displacement is given to the phi 2 displacement as 1 unit, like 1 centimeter or 1 meter or something like that, 1 unit displacement is given. What could be the displacement to the next one? So that is what, see, if I give a phi 2 1 is equal to 1, let us say if I substitute here, with this phi 1 is equal to, if I bring this minus 1 other side, it becomes plus 1 by 1.619 becomes 0.617. That means phi 2 which is the, see, 2 notation we are using for the second mass, which is in the top in our building model. Phi 1 means displacement x1. This comes from the displacement x1, which is in the first floor, not the topmost floor, first floor, right? So one notation, the phi 1 notation for the first one. So if for the topmost floor, if I give a displacement as 1 unit, but the middle floor will displace by 0.617 only with this frequency, what we got omega n1. For omega n1, with that frequency, the displacement mode will be like that. You'll understand that. I will draw the figure also. And before that, let me complete the second mode for lambda 2, 2.618 for second mode. I mean, what I'm trying to do is a natural frequency or second natural frequency I'm using. But once again, instead of doing that omega n square and all, lambda 2 itself, I'm using it is easy for a calculation purpose. So now we have 2 minus lambda 1. Instead of lambda 1, I'm putting the lambda 2 now. Minus 1, 1 minus lambda. That lambda is lambda 2 now. As such, now phi 1 instead of 1, 2, and phi 2 instead of 1, now it is 2. So this is second mode. For the second mode, I'm using a 2 notation for both the phi's is equal to 0, 0. So now I substitute that lambda 2 here, and then multiply the first minus 0.618 into phi 1, 2, minus 1 into phi 2, 2 is equal to 0. And here also, if I put phi 2 is equal to 1, substituting phi 2 equal to 1, what is the value of phi 1? 2 is equal to minus 1.618. That means the topmost floor will displace by 1 unit, the middle floor will displace in the opposite direction, minus sign, no, in the opposite direction, minus 1.618. You will see the modes of vibration. So this is what the figure. So please try to understand this. The first mode with the first natural frequency omega n1, and see the topmost floor phi 2, we have given a one unit displacement, right? So with that, middle one, this x1, this mass will displace by 0.617 only. That's what we got in the first thing. Then for the lambda 2, I mean for the second natural frequency, topmost floor I gave only 1 unit displacement, but middle floor will displace by minus 1.61. That means if I take the positive value in the right hand side, negative value in the left hand side. So this building will vibrate like this. The shape of vibration like this. See, the first mode of vibration, if you see, and how the displacement of both the masses. So topmost mass, if it displaces by 1 unit, and middle mass will displace only 0.617 in the only one side. So right hand side and also left hand side. It is not only right hand side only. See, from the center, I don't know whether I can do it. See, the second mode, if you see, top will move right and the middle will move in the left hand. Similarly, whenever the topmost mass will move in the left hand side, but middle mass will move in the right hand side. Simultaneously, it happens. The moment it is like a shaking kind of stuff, like a snake type of stuff, right? So I don't know. See, in the class, I would have explained you in a better manner. I don't know how many of you understood. Okay. Could you see me? My hand? Hello? Hello?
Yes, sir.
Okay, you can see this. Imagine that the topmost road is here, mass, and middle mass is here. So entire building will move like this. Okay, so topmost displacement is more and middle displacement is less. It is not only vibrating towards right hand side what I shown in the figure, it also vibrates in the left hand side like this. So the displacement will be like this. It vibrates in this fashion, right? It is not only displaces in the right hand side, it also displaces in the left hand side. But unit of displacements are like that. The left, I mean, topmost is 1 unit and the middle one is 0.617, something like that. In the first mode of vibration with that natural frequency of omega n1. With the second frequency, what happens is, see, the middle mass will move left hand side. At the same time, top will move right hand side. So it is like a snake kind of structure. It moves this way. So the oscillation will be in this fashion. It is not simply like this. Understand that the oscillation will be like this. So both left hand side and the middle mass will move right hand side. Topmost mass will move if it is in the left hand side. Middle mass will move in the right hand side by 1.617. What is shown? What we have got it like this. So finally, the vibration of the second mass is like a snake kind of stuff. Okay, hope you understood what I'm trying to say. Is it clear? So that modes of vibration is about with that particular natural frequency and building masses at various flows, how it displays that vibration, how it happens. So the first mode is always only one side, only one side, completely one side first mode. But second mode is in different ways, like a snake kind of movement like this. Okay, so my middle floor mass will move on one side and topmost floor will move in the right, other side. So at a time like this, then this way and this way like this. I hope you understood what I'm trying to say. Okay. Any doubts? Anyway, so please try to follow, and I will today itself I will upload this material in the Google Classroom. So try to solve it.